Hello, and welcome back to our channel. Ever feel like time is just slipping through your fingers? Or that it's a constant ticking clock, the same for everyone, everywhere? Well, get ready to have your mind blown, because today, we're diving deep into one of the biggest mysteries in the universe, the true nature of time. What if I told you that the time on your watch isn't as absolute as you think? That it can stretch, shrink, and might not even flow in one direction at the quantum level? Let's start with a genius you've all heard of, Albert Einstein. Over a century ago, he completely revolutionized our understanding of space and time. He proposed that they aren't separate things but are woven together into a single fabric called space-time. And here's where it gets wild. This fabric can be warped and stretched by gravity and speed. This leads to a phenomenon called time dilation. In simple terms, the faster you move through space, the slower you move through time. Imagine two twins. One stays on Earth and the other hops on a spaceship traveling near the speed of light. When the space-traveling twin returns, they will have aged less than their sibling who stayed behind. It sounds like science fiction, but it's science fact. This isn't just a theory, it's been proven. Scientists placed incredibly precise atomic clocks on airplanes and flew them around the world. When they landed, those clocks were slightly behind the ones left on the ground, exactly as Einstein predicted. This effect isn't just some abstract concept for physicists to ponder. It has a real-world impact on your daily life. Every time you use GPS to find your way, you're relying on Einstein's theories. The satellites orbiting Earth are moving much faster than we are, and they also experience weaker gravity. Both of these factors cause their internal clocks to run at a slightly different rate than clocks on the ground. If engineers didn't constantly correct for this time dilation, your GPS would be off by several miles within a single day. So, the next time you navigate to a new restaurant, you can thank Einstein for getting you there accurately. This idea that time is relative completely shatters our everyday intuition. It means there's no single universal now across the cosmos. What you experience as the present moment is different for someone moving at a different speed. It forces us to ask, is our perception of a steady flowing river of time just an illusion created by our specific circumstances here on Earth? But Einstein's relativity is just one piece of the puzzle. When we zoom down to the bizarre world of quantum mechanics, the physics of the very, very small, the concept of time gets even stranger. In our classical world, things happen in a clear sequence. You drop a glass, it falls, then it shatters. The cause comes before the effect. But at the quantum level, this clear-cut order can become fuzzy. In the quantum realm, particles like electrons can exist in multiple states at once, in a superposition. Time itself might not be the smooth, continuous line we imagine. Some theories suggest that at the smallest possible scale, known as the Planck scale, time might break down into discrete individual ticks, like the frames of a movie. In this view, the smooth flow of time we experience is just an emergent property, an illusion created by these countless tiny moments blurring together. Furthermore, most of the fundamental laws of physics are time-symmetric. This means the equations work just as well whether time is running forward or backward. If you watch a video of planets orbiting the sun, you can't tell if the video is playing forward or in reverse. It looks perfectly natural either way. So if the basic laws don't care about the direction of time, why do we? Why do we remember the past but not the future? Why do eggs break but never unbreak? This brings us to the arrow of time. The most popular explanation for this one-way street is a concept called entropy. Entropy is, in simple terms, a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system, like our universe, can only increase or stay the same. It never decreases. Think about your room. It's much easier for it to get messy, high entropy, than it is for it to spontaneously become tidy, low entropy. The universe began in a very low entropy state, incredibly hot, dense and uniform at the Big Bang. Since then, it has been constantly expanding, cooling, and becoming more disordered. Stars burn out, structures crumble, and energy spreads out. This relentless march towards greater disorder is what we perceive as the forward flow of time. Our memories, the process of aging, the entire story of our lives, are all tied to this increase in entropy. The arrow of time isn't a fundamental property of time itself, but rather a consequence of the starting conditions of our universe. So what does this all mean? Time isn't a simple clock ticking away in the background. It's a dynamic, flexible, and deeply mysterious part of the fabric of reality. It's warped by gravity, stretched by speed, and its very direction might just be a story told by the increasing disorder of the cosmos. Scientists are still grappling with these ideas, trying to unite Einstein's relativity with the weirdness of quantum mechanics to find a final theory of everything. Perhaps in that theory we'll finally understand what time truly is. Is it fundamental? Or does it emerge from something even deeper? We've journeyed from Einstein's spacetime to the quantum fuzziness and the cosmic arrow of entropy. It's a lot to take in, but it shows how wonderfully strange and fascinating our universe is. The familiar tick-tock of the clock hides a profound mystery that touches on the very beginning and ultimate fate of everything. What do you think? Is time real or just a stubborn illusion? Let me know your thoughts in the comments below. It's a topic I love discussing. If you enjoyed this journey beyond the clock, please give this video a thumbs up and consider subscribing to the channel for more explorations into the biggest questions in science. Thanks so much for watching, and I'll see you in the next one.